Okay, so for lesson 5, we're going to talk about theoretical and experimental probability, but we're really going to talk more about theoretical probability. So I've already kind of filled out all of your vocabulary words for the beginning of this lesson, and I'm just going to kind of talk about this right here, and that'll make the vocabulary words make a lot more sense. So here's how these terms apply to rolling an even number on a numbered cube. So the event that you want to happen, so the event is rolling an even number. That's what you want to happen. So whenever you roll a die, you want it to be an even number. Now, the sample space is all possible outcomes. So what that means is if you roll a die, a 6-sided die, your outcomes are 1, 2, 3, 4, 5, or 6. Okay? Now, of those outcomes, the only ones that are actually even are 2, 4, and 6. So those are your favorable outcomes. That's what you want to happen. That's what you want to roll whenever you roll your die in order for it to be an even number. So the probability of an event or theoretical probability tells you how likely it is that the event will occur. So you can find probabilities by reasoning mathematically or by using data collections from an experiment. So that's kind of like flipping a coin. A lot of you know if you flip heads or tails, you have a 50% chance of being right if somebody told you to flip heads or tails. So that's where this probability comes in. Another place that you see it in real life is like a scratch off at the gas station. On the back of those scratch offs, a lot of the times they have your probability of winning, okay? Like winning the lottery. It's not a very good probability, but it is a probability. So, in this numbered cube example above, the outcomes in the sample space are equally likely to occur. So when all possible outcomes are equally likely, you can find the theoretical probability of an event using this formula. So you're talking about the number of favorable outcomes. So if we look above, the only numbers that are favorable are 2, 4, and 6. So that's 3 possible favorable outcomes over all possible outcomes. So that's your sample space. That's how many different outcomes you can get. So there's actually 6 of those. Okay, so your chances of rolling an even number, if you go ahead and you reduce this fraction, is going to be 1/2. Okay, so you can write the probability of an event as a fraction like we did above. You can also write it as a decimal. So like this would be 0.5 as a decimal if you took 1 divided by 2 in your calculator. Or you can write it as a percent. So the way we do this is if you take 1 divided by 2 and get that 0.5, but then if you multiply that by 100, because it's out of like 100%, that's actually going to give you 50. So that's going to be the percent that it's likely that you have one of those favorable outcomes of 2, 4, or 6. Okay, so the probability ranges from 0 to 1 as a decimal. So 0 meaning it's like impossible for that to happen. So in today's world, if I said, what's the probability of you seeing a real live dinosaur? We're going to say that probability is impossible because of the fact that dinosaurs are extinct. Okay. The other side of the spectrum would be 1, meaning it's certain. So that'd be like me saying, what is the probability of flipping heads or tails? Well, there's only 2 options on a coin, heads or tails. So if you want to know the probability of flipping either one of those, you're going to end up with a probability that's a 1. So it's 100% likely to occur. Okay, somewhere in the middle, equally likely to occur or not occur. So that middle ground is at 0.5. So that would be like flipping a coin and saying, okay, I want you to flip heads. Okay, there's a 50% chance that you're going to flip heads, theoretically. Okay, so that's just kind of giving you an idea of all of the possibilities whenever it comes to probability. Okay, so we're going to go ahead and find some probability here. So it says our solar system's 8 planets in order from least to greatest distance from the sun. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, so you will randomly draw one of the names of the planets and write a report on that specific planet. So it says, what is the theoretical probability that you will select a planet whose distance from the sun is less than Earth? So we only want to talk about the planets that are closer to the sun than Earth. So we're only talking about Venus and Mercury. So we want to know how many favorable outcomes do we have? Well, the only 2 that we have are Mercury and Venus. So that's going to be 2 out of the total amount of planets. And so we have 8 total planets here. So if I wanted to write this in reduced form, I'm going to reduce that fraction to make it 1/4. Now you could also write it as a decimal, which would be 0.25. And if you multiply that by 100, you'd get a percent of 25%. So this answer, or this answer are all okay with me. I don't want 2/8 just because it is not reduced. Okay. So this time it says in example 1, what is the theoretical probability that you will select a planet whose distance from the sun is greater than Earth's? So this time we're talking about all of the planets who are further away from the sun than Earth. So we have Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, so this time we have 5 planets that are further away. So that's our favorable outcomes, 5 of them. Okay, out of the total of 8. Now we actually cannot reduce that any. So if we take 5 divided by 8, that would be our fraction answer. But this 5 divided by 8 would give you 0.625. That would be your decimal answer. And then if I told you I wanted it as a percent, you can take that decimal answer, multiply it by 100, and that gives you 62.5%. Okay, so any of these 3 answers would work for me if it does not specify in the directions. Okay, moving on to number 3. So it says you roll a 6-sided die with the numbers 1 through 6 labeled with 1 on each face. So basically just a regular die. Find the probability of each event. So if you want to roll a 3, and you have the options of rolling a 1, 2, 3, 4, 5, or 6. What it's asking basically is, how many favorable outcomes do you have? How many times out of these 6 numbers, how many of them are 3? Well, there's only 1 3. And how many total possibilities? So how many different numbers could you roll? Well, you can only roll 6 different things. So your probability would actually be 1/6. And I'm just going to leave it as a fraction for now. Okay. Then it says event B, you want to roll a 7. Well, if you look at your possible outcomes, is there a 7 there? And there's not. So if you wanted to roll a 7 on a 6-sided die, that's impossible. You can't do that. So that's going to be a probability of 0. You could say 0 out of 6, but that still just gives you 0 whenever you reduce. Then for event C, it's saying a number less than 5. So we're talking about 4, 3, 2, and 1. So there are 4 numbers that are less than 5 out of 6 total numbers. So we have a fraction of 4/6, or the probability of 4/6, but we want to go ahead and reduce that to 2/3. Now if we look, it says a number greater than 3. So let me see if I can erase just the lines underneath. There. Okay. So it says a number greater than 3. So our numbers greater than 3 are 4, 5, and 6. So there are only 3 numbers greater than 3 out of 6 total numbers. So if we reduce that fraction, we get 1/2. Okay. Oh, man. I got rid of the 6. There we go. Okay, a number less than or equal to 7. Well, we know we can't get 7, but we also know that we can get a number less than 7, which is every single one of these numbers. So if you have 6 that are less than 7, out of 6 total possibilities, 6 over 6 just reduces to 1. So that is certain that you are going to get a number that is either less than or equal to 7. Okay, rolling a 0, 1, 2, 3, 4, 5, and 6, there's not a 0 there. Okay, so the probability of rolling a 0 is 0 out of 6, which just reduces to 0. Okay, the next thing we're going to talk about is actually experimental probability, and that's based on data collection from repeated trials. So basically that'd be like if I was going to draw a name out of a hat, and there were the same number of each name, if I drew out a name and continually did that, the data that I collected could be used in order to find experimental probability. So the number of times the event occurs over the number of times the experiment is done. Okay, so we're going to kind of look at an example with number 4 here. So it says a pond contains 3 types of fish: bluegills, redgills, and crappies. Each fish in the pond is equally likely to be caught. So you catch 120 fish total. So that's an important number here. 120 fish, and record the type each time you catch the fish. So each time you release the fish back into the pond. The frequency distribution shows your results. So if you catch another fish, what is the probability that it will be a bluegill? So we want to know the probability of a bluegill. So I'm only going to be looking at this row here. So the number of times that this event has occurred is 39 times. So we caught a bluegill 39 times. And then it says the number of times the experiment was done. So basically how many fish this person caught. And it told us in the directions that they caught 120 fish. So that 39 is going to be out of 120. Okay, so that is going to be the probability that you catch a bluegill on your next catch. For number 5, it says an insurance company conducts a study and determines that in every 100 claims, 4 are fraudulent. What is the probability the next claim the company processes will be fraudulent? So basically, this is saying number of times the event occurs. Well, number of times that we have a fraudulent claim, and that's going to be 4 times. We've had a fraudulent claim 4 times. Then it says the number of times the experiment was done. So how many claims in total? And that right there is saying 100 claims. So we're saying 4 over 100, and that can reduce to 1 over 25. So that's going to be the probability. Okay, let's look at number 6 and 7. It says, after receiving complaints, the skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds no defects in 992 of those skateboards. So what that basically is telling us is if you take 1,000 minus 992, that means that 8 of these skateboards have a defect of some kind. So 8 skateboards with defect. Okay, what is the probability that a skateboard selected at random has no defects? So write the probability as a percent. Okay, so we want to make sure that we know to make this a percent. So we want to know how many of the skateboards didn't have a defect to begin with? So we end up with 992 skateboards had no defect whenever they went through and checked. And they checked how many total skateboards. So they checked 1,000 skateboards. So if I go and I take 992 and divide that by 1,000, that will give me a decimal of 0.992. With that being said, it still wants it to be a percent. So I have to take that 0.992 and multiply it by 100. So I end up with 99.2% of the skateboards do not have a defect. So our answer would be 99.2%. So it says, suppose the manufacturer, an example, it should say example 6, sorry about that, inspects 2,500 skateboards. There are 2,450 skateboards with no defects. What is the probability that a skateboard selected at random has no defects? Write the probability as a percent. So this time, we're just upping the numbers. So we had 2,450 with no problems, okay, out of a total of 2,500 skateboards. So we want to know, it says write this as a percent again, so we want to put that into a decimal, which is going to be 2,450 divided by 2,500, and we get 0.98. And then if you take that times 100, you end up with 98% of the skateboards having no defects. Okay. So, for number 8, it says you survey a sample of 1,000 employees at a company and record the age of each. The results are shown below in a frequency distribution. If you randomly select another employee, what is the probability that... So we want to know the probability that they're aged 25 to 34. So here we're looking at 25 to 34. And there are 366 employees that are aged between that range. So we have 366, and we wanted that out of the total, and it says the sample is 1,000 employees. So we're taking that out of 1,000. So if I'm just going to put these as decimals since we haven't done that yet. So 366, and then divide that by 1,000, and we get 0.366. Okay, so then for letter B, it says age 25 to 44. So here's our 25 and here's our 44. So we're looking at both of these groups now. So we're looking at both of these numbers. So we're taking that 366 and we're going to add in 233, which gives us 599 people out of 1,000. Okay, so if we divide those two, we end up with 0.599. Okay, for part C, it says, what's the probability that the person is less than 45? So here's our 45. So we want everything less than that. So we're looking at these 3 age groups, which means that we're looking at these 3 frequencies. So we're going to add all the frequencies together. So 54 plus 366 plus 233, and we get 653 out of the total number they sampled of 1,000. So if we go ahead and we divide, we end up with 0.653. Okay, now for D, it says greater than 44. So 44 is here, and we want everything greater. So we're looking at these 3 categories, and then we're looking at these 3 frequencies. So we have to add all that together. So we have 180 plus 125 plus 4. And that gives us 309 people are greater than 44 out of the people they surveyed, and that was out of 1,000 people. So if we were to make that into a decimal, we would have 0.309. Actually, I don't want to erase that. I don't know why I did that. All right. So, moving on. You can also use experimental probability to make predictions. Predictions are not exact, so round your results. So, if we look at number 9, it says you ask 500 randomly selected households in your town if they have a dog. Of the 500 households, 197, so I'm going to go ahead and underline some key information. 500 households, 197 respond that they do have a dog. If your town has 24,800 households, about how many households are likely to have a dog? So, what we want to do here is we want to take this 197, because that's how many people had a house or had a dog out of the households that were surveyed. And we want to take that out of the total of 500 people sampled. Okay, and we want to figure out what that number is. But let's go ahead and take that then. Once you figure out what that decimal is, you're going to take that and you're going to multiply that by 24,800 households. So basically what we're doing is we're finding the probability that they do have a dog, and we're multiplying that by the total population. So we're going to say 197 divided by 500. That decimal, we're going to then take that times 24,800. That gives us approximately 9,771.2 households that have a dog. Now, clearly, we can't have 0.2 of a household that have a dog. So, in order to kind of keep this more precise, we're going to round to the nearest whole number. And since this 2 is less than 5 or less, basically, less than 5, we're going to go ahead and keep that 1 the same. So, we're going to have 9,771 households that have a dog. For number 10, it says a manufacturer inspects 700 light bulbs and finds that 692 of them, they work. So there are about 35,400 light bulbs in the manufacturer's warehouse. About how many of the light bulbs in the warehouse are likely to work? So we're doing the same process we just did. So we're saying that 692 of the light bulbs worked. And that was out of a total of 700. So once you get that decimal, you can then take it by the total number of light bulbs in the entire warehouse. So 35,400. Okay, so I'm going to take that 692 and divide by 700, and I get this really big long decimal. So once I get that decimal, I'm going to go ahead and I'm going to multiply that by 35,400. And that leaves me with approximately 34,995.4 light bulbs that work. Now, with this being said, again, we can't have 0.4 of a light bulb that work. So we're going to just go ahead and round that answer to the nearest whole number. So 34,995 light bulbs that work. Okay, so the blank of an event, that would be the complement of an event. Consists of all outcomes in the sample space that are not in the event. So basically what that's saying is if I wanted to roll, I wanted the probability of not rolling an even. number on a 6-sided die. That would be saying basically I want to know the probability of rolling an odd number instead. So the possible outcomes for rolling number cubes are 1, 2, 3, 4, and 6. Or I'm sorry, 4, 5, and 6. The outcomes for rolling an even number are 2, 4, and 6. So the outcomes of the complement of rolling an even would be rolling those odds, 1, 3, and 5. Okay, so the sum of the probabilities of an event and its complement is 1. So the probability of an event plus the probability of not that event equals 1. So if we kind of rearrange that a little bit, we can say this is also a good way to find this. So the probability of not an event is equal to 1 times the probability of the event. Okay. So it says in a taste test, 50 participants are randomly given a beverage sample. So there are 20 samples of drink A, 10 samples of drink B, 10 samples of drink C, and 10 samples of drink D. So what is the probability of a participant not getting drink A? So we don't want any drink A's. It can be anything but a drink A. So we have 10 samples of drink B, 10 samples of drink C, and 10 samples of drink D. So if we look at these, we have a total of 30 drinks that are not drink A. So we're taking 30 and we're going to divide that by the number of total drinks. So we have a total of 50. Okay, so if I want to know this probability, this is definitely not in simplified form. So 30 over 50, that's going to reduce to 3 over 5, which also equals 0.6 or 60%. Okay. Suppose a taste test is repeated with the same number of samples of drink A, but more samples of other drinks. What happens to the probability of it not being drink A? Well, if we end up adding more to all of the other samples, so adding more to the 10s, that probability is actually going to go up. So it's actually going to be answer A. Okay. So so moving on, I don't know why these days are here. We're going to look at what we call a two-way table. So it shows frequencies for two different categories simultaneously, which I have such a hard time saying. As a class, collect the following data. Since we are not actually in class, I'm going to go ahead and just give some numbers here. So what this is saying is if I put in, let's say, 15, 2, 0, and let's do 10. Okay, what this is saying is why did I put 27 there? So what this is actually telling us is that 15 people like dogs more than cats and got enough sleep. So you kind of follow your rows and your columns until you get to this number. Okay, like this 2 would say 2 people like dogs more than cats and did not get enough sleep last night. Okay, so that's kind of the gist of a two-way table. Okay, so the marginal probabilities are probabilities involving blank categories. The marginal frequency is found along the outside of the two-way table. Okay, and marginal probabilities are probabilities involving, let's see, 2 categories. Why can I not write here? I'm sorry, 1 category. Losing my mind. Okay. If a person is randomly selected from this class, basically we want to find the marginal probability that the person likes dogs more than cats. So we're looking at only the people who like dogs more than cats. And if you look, there's 15 and 2 of those. So there's a total of 17 people who like dogs more than cats. Okay. But we want to know how many is that out of. So that class total for this made up class would be 27. So we have 17 out of 27 people like dogs more than cats. Okay, and it says state your answer as a reduced fraction. 17 over 27 doesn't reduce any further. I'm deleting other stuff too. Okay, so find the probability the person got enough sleep last night. So basically, then we're looking at the people who got enough sleep. That's the only people we're looking at. So total, if I look down here, there's 15 people out of a total of 27. And it says state your answer as a decimal, rounded to the nearest hundredth if necessary. So we're going to take 15 divided by 27, and we get a big long decimal of 0.5555, and it keeps going. Okay, but hundredth is to the second place. So we're going to look and we're going to move our decimal, or I'm sorry, we're not moving our decimal. We're looking 2 here. So we're looking at this number and this number. And since this 5 is 5 or greater, we're going to round that up to 0.56. Okay, for number 15, it says, what's the probability the person does not like dogs more than cats? So we are only looking at the people who do not like dogs more than cats. And that's a total of 10 people out of the total number of people of 27. And it says state your answer as a percent rounded to the nearest percent if necessary. So we take that 10 and divide it by 27, and we get this big long decimal. I'm not going to write the whole thing out. But once we get that big long decimal, we're going to take that times 100, and we end up with 37%. Joint probabilities involve 2 categories. Okay, and the joint frequency is found where the 2 categories join together. So we're actually going to be looking at 2 different categories at the same time. So basically for number 16, it says find the probability the person likes dogs more than cats and did not get enough sleep. So we're looking at likes dogs more than cats. So we're looking at these 2 numbers, but then we're saying they did not get enough sleep. So then we're only looking at this right here at 2. So we're going to look at 2 out of 27. And it says state your answer as a percent. So we're going to take that 2 divided by 27. And we get 0.07407, a big long decimal, and I'm going to take that and multiply it by 100. So we end up with 7.4%, and that is rounded to the nearest tenth. Okay, for number 17, it says the person does not like dogs more than cats and did get enough sleep. So basically, we're looking at here. And I think I just got rid of another number. And now I forgot what I was finding. The person does not like dogs more than cats and did get enough sleep last night. So doesn't like dogs more than cats and did get enough sleep. So we kind of follow this down and we follow this over and they meet here at 0. Okay. So 0 out of 27 people is our probability, and it says state your answer as a decimal. Well, 0 divided by 27 is just 0. Okay. Number 18, it says, what's the probability the person likes dogs more than cats and did get enough sleep last night? So we're looking at likes dogs more than cats, and did get enough sleep last night. So if you follow this over, follow this down, they meet right here at 15 out of 27. It says state your answer as a reduced fraction. That is not reduced, actually. We're going to end up with 5/9. Okay, let's see, last page. So in 1912, the luxury liner Titanic, in its first voyage across the Atlantic, struck an iceberg and sank. Some passengers got off the ship in lifeboats, but many died. The two-way table gives information about adult passengers who survived and who died by class of travel. So basically, this is saying class of travel is your first, second, and third class people. Okay, so back whenever the Titanic set sail, a lot of your first class were in the nice luxurious rooms. Your second class was down a little bit lower. And then your third class, if you guys have ever seen the Titanic, was like on the very lower end of the boat. So that's where it would have probably started filling up with water first. So that could be why you see a lot of people from third class that actually died. Okay. Over on the left side, you have survival status. So you have your survived and died, and then you have your totals. So what is the probability that the passenger just survived? So here you're looking at all of your survival people, okay? And that gives you a total of 442 people survived on the Titanic out of the total people that were on the Titanic of 1,207 people. It says state your answer as a percent to the nearest tenth. So what you have to do, again, is divide that 442 divided by 1,207, and we get a 0.36619, a big long decimal. And if you want to get it as a percent, you have to multiply that by 1,000, and we get 36,000. I'm sorry, you multiply it by 100 to get the percent, and you get 36.6%, and that would be rounded to the nearest tenth. Okay, then it says, what is the probability that the passenger survived and was traveling third class? So we're looking at survived, and we're looking at traveled third class. So we're going to kind of follow this over, and we're going to follow this down, and those meet right here at 151. And that's out of the total, again, of 1,207 people. Okay, state the answer as a percent to the nearest hundredth this time. So again, we take that 151, divide by 1,207, and we get 0.12510, and it keeps going on and on. So multiply that by 1,000, and we get a percent of 12.51%. And that's rounded to the nearest hundredth. For 21, it says, what is the probability that the passenger survived and was traveling first class? So again, we're looking at your survived people. We're looking at first class, and we're going to follow over and down until we meet at 197 out of 1,207. This gives us, asking us for a percent to the nearest tenth. So we're going to take that 197, divide that by 1,207. We get a decimal of 0.16321, and it keeps going on. But we're going to go ahead and we are going to multiply that by 100 to get our percent of 16.3% to the nearest tenth. What is the probability that the passenger was traveling second class? So now we're just looking at one category. We're looking at second class people. And we go all the way down to the total of 261 people were traveling second class. And that's out of the total of 1,207. This says round a decimal to the nearest thousands. So we're going to go ahead and divide these two numbers, 261 divided by 1,207, and we get 0.2162. Now, since it's talking about thousands, we have tenths, hundredths, thousandths. So we have to look at this 2, and since it's less than 5, we're going to say our answer is just going to say 0.216. All right, our last question here says, what is the probability that the passenger was traveling second class and survived? So we have our second class people, and we have people who survived. So we're following this over, we're following this down, and we get a total of 94 people whenever we meet at 1,200 out of 1,207. Now this says state your answer as a decimal to the nearest hundredth. So again, we're going to divide that 94 divided by 1,207, and we get 0.0778. But it wants it to the hundredths. So we have tenths, hundredths. We need to look at the number after that, and we have a 7, which is 5 or greater, which is going to boost this 7 up to an 8. So we have 0.08. And I think